Hello and welcome. Today I will show you how to implement a simple visual servoing control scheme. Visual servoing is the practice of controlling a system using camera information as feedback. In this particular video, our system is going to be a 2 degree of freedom system, which will be a pan-tilt camera. Our target, which will be detected based on its color, will move along a path in our environment. And our camera will detect the object using color-based object detection, and it will then adjust the joint velocities to match the velocity of the target. In addition, I'm going to also show you how to use this debug window, which allows you to export information while you're writing your code. All right, so let's begin. We begin this tutorial with a new file, which you can access by selecting File, New Scene. The first thing we're going to do is we're going to implement a path and then model the moving target. So right-click anywhere on in the scene, select Add, and then Path, and then Segment Type. So now you've added 2 points. Now we have to go ahead and add a couple of more points to the path to make it more exciting. Right-click on the path, select Edit, Edit Modes, and select Enter Path Edit Mode. In here, you will now be shown your 2 points and a list of points over here. So, select your last point, right-click, and select Insert New Control Point after selection. This will create an additional point right on top of where your old point used to be. So now we have to go ahead and move the point. Select the object item shift with your path point 3 selected, and then move it around anywhere. And this should be good for now. And then repeat this a couple of times until you have a path that is somewhat exciting and something that your target will follow. After you have modeled a couple of points, we want to make this path cyclical, meaning the object should follow on it repeatedly. So select Path as Closed so that the last point is going to be reconnected with your first point. Once you're done and your path is how you want it, press X, and then it'll ask you if you want to apply these changes, and then select Yes. So now you have modeled a path. The next step is to model the target, which we will just make a simple sphere. Right-click anywhere on the scene, select Add, Primitive Shape, and then we'll select a sphere. And then we select a sphere of size of radius 0.1 meters. So now you've modeled the sphere. Let's rename the sphere and call it our target. And the other thing that we want to do is we want to change the color of the target. So double click on the cube and then select Adjust Texture, Adjust Outside Color, Adjust Ambient Component, and here you get to choose RGB or in Hue, Saturation, and Luminosity. So we want to make this bright red, so let's select red 1 and then green and blue 0. And now you've modeled the target. Now that we've modeled the target, we want to make the target follow our path. The way we do that is with the aid of something that's called a dummy object. Right-click anywhere on the path, select Add, and then Dummy. By itself, the dummy doesn't do much. It's just a point and a direction. However, it's a very useful object when it comes to things like calculation or path following. So we want to attach the dummy to our path, so we select the dummy and then drag it onto the path. This makes the path the parent object of the dummy. And now we want to make the target, make the child, or make the dummy the parent of the target. So you select the target and then drag it over. The next thing we're going to do is we're going to set a velocity for the dummy to follow. Double click on the path and then select here under target nominal velocity, select 0.1 meters per second. If you run the script now, you'll find that the dummy moves along the path, yet the target is not moving. What we have to do next, we have to double click on the target and then select common, show dynamic properties, and then select the static. This means now that the object won't interact with anything within the field. So we also have to double click on the dummy object and then select follow parent path orientation, follow parent path. So now when you run it, you'll find that our target is following the dummy along the path. So now you've modeled the path itself as well as the target that moves around the path. The next step will be to model the camera itself. We said that the camera will be a pan tilt camera, so we will need a couple of revolute joints that make up the camera itself. Right click anywhere in the field, select add, then joint, and then revolute. Now it creates a revolute joint that is upright. This is going to be the base of our camera and it's going to be our yaw direction. So let's drag it somewhere out of the way. Select object item shift with the revolute joint selected, and then let's move it somewhere next to the path. Alright, we're also going to rename this because it'll be our yaw direction. The next thing we're going to have to do is model the pitch direction. Again, right click, add, joint, revolute. Add, joint, revolute. Alright, so now we want to align at least one of the axes. Actually, we want to position this revolute joint above our yaw. So what we do is with the revolute joint selected, we select also the yaw and select object item shift. And then here we want to apply the X and the Y coordinates. But as far as the Z coordinates are concerned, we're going to lift it up, let's say by 0.3 meters. And then when we click translate selection, it should translate along the world Z coordinates. And over here you can see which direction that will be in. Oh, actually, I will undo that. Because I had both of them selected, it moved both of them. So now just select the revolute joint, select again translate selection. So now you have the revolute joint positioned above the yaw joint. So the next thing we want to do is we want to rotate it about 90 degrees around its own X coordinate. So select on frame around X and then select 90 right here. And now you will see that this is kind of the yaw rotates it back and forth, and which kind of would translate into the left to right movement of your head. And this upper revolute joint, which I will call pitch, corresponds to the up and down motion of your head. And again, we want to make the pitch the child of the yaw so that it moves with the other object. The other thing that we have to do, we have to set the mode of the joints, and rather than in torque force mode, let's select joint is in motion mode. And we do that for both of them. So now we have the base of our camera. The next step will be to add the camera itself. Now right click anywhere on this base, select add, and then rather than camera, we're actually going to add a vision sensor. And we're actually adding a perspective type vision sensor. So now we've added a camera right here, and we want to align it with our joints. So select the vision sensor and then pitch, and then again go into the object item shift mode, and then we want to apply the X, the Y, and the Z coordinates. So now the camera is kind of attached to the pitch joint, and maybe just in case, let's elevate it ever so slightly so that there is no kind of interference with of the vision sensor, so that we don't all of a sudden appear inside of the joint. So I'm going to just shift it up just a little bit. Oh, again, I want to shift up just the camera itself. Now this might not be a problem, but just in case. Alright, so now our camera is currently looking up. This pyramid, this blue pyramid, kind of indicates where we're looking. The Z-axis is the camera optical axis. So let's make the vision sensor the child of our pitch direction, and let's rotate our pitch direction along its own Z coordinate. So what we do is we select pitch and then object item rotate, and then around its own frame we want to rotate it around the Z by about 90 degrees. So now the camera is kind of looking forward. The thing is, if you were to run it now, well, okay, we need to kind of add a window that shows us what the camera is seeing. So for that, let's add a floating window. Select, right click anywhere in the space, select add, and then a floating view. With the camera selected, right click the floating view, select associate view with selected vision sensor. So now everything the vision sensor is seeing will show up in here. If you run it now, you will find that it's only showing black. The reason for that is that there is actually no object within that pyramid, because that pyramid indicates how far it can see. So now let's play around with the settings a little bit. Double click on the camera icon, and then here where it says near far clipping distance, it indicates how near to the camera it clips it off and what's the maximum distance that it can detect. So maybe select 3.0 meters for now. Alright, so now we run it, and now we can see that our camera is actually on its side. And let's fix that by rotating it around 90 degrees about its Z-axis. Alright. So now let's try running it, and then now we find that we're upside down. So then again, let's try 180 degrees. And now we're right side up. Alright. So, even though our object is entering the image, we still can't quite see it. Let me actually adjust the camera orientation to look down a little bit more. So what I do is I will rotate the pitch by just a little bit more around its own Z-axis by maybe 20 degrees. That way we're kind of looking down. So right now, even though the object is in the image, it's not showing up on the vision sensor. That's because we have to adjust the properties of the target itself. That would be right here under Object Special Properties, and I believe that it's measurable. Let's try it out. Nope. And try the renderable. Alright, and now the object is showing up. One thing you will notice, I'll just pause it right here, is that the resolution is quite bad. And well, what we have to do is we have to adjust the resolution of the vision sensor itself. Double click on the vision sensor and it will tell you here resolution in the X and the Y direction. So let's change it to something like 200. And when you change it to something like 200, it will tell you that it only supports powers of 2 when it comes to the resolution. So let's select 256. And I guess the higher the resolution, the slower, the more taxing it will be on your computer. Alright, so now you have modeled the camera and the moving target. Now you have to go on and define the object detection method. So, for the object detection method, VREP has a bunch of built-in functions. If you double click on the vision sensor, and over here there is image processing and triggering, and over here you get access to a whole load of filters that you can use to detect objects and manipulate the images themselves. So, when you click on the Show Filter dialog, you will see that there's currently two entries. There is original image to work image, meaning it takes the image from the vision sensor, and then work image to output image. So here you kind of only have two steps. And you can extend this by adding certain filters that will sequentially manipulate the image as you go on. So let me kind of run this. Right now it takes the original image, makes it into work image, does nothing to the work image, and sends it to the output image. Let's try a couple of filters just to kind of show you the extent of the functionality. So one thing we can do is we can, for example, rotate the work image or shift the work image, meaning we can shift all the objects to the side. You can also work with buffers. That's a little bit outside of the scope. You can resize the work image. For now, let's try a 3x3 filter on the work image. And what we do is we put this 3x3 filter in between the work image and the output image, so that the output image will be the filtered image. So this is kind of like a Gaussian blur, and you will see that now everything is a little bit more blurrier than it was before. This is actually just something that is used for noise removal. So let's delete this and kind of show you a 5x5 filter, and this makes it a little bit more blurry than it was before. Alright, so since we're using color-based object detection, we have to select the selective color on work image. So what we want to do, we want to take everything out of this image that is not our desired color. Luckily we selected red, which has a very distinct color to itself. So under selected colors and which one to keep, we're going to select red, and we'll select 1, because that's when we were defining the color we selected 100 for red, green, blue. So we want to make sure that we keep, and here you select what you want to keep or whether you want to remove it. So we want to select everything within 0.2. And green saturate and green and blue, we want to doesn't matter what the color is, so we'll select 0.5. So now it will remove anything that is outside of these bounds. So when it comes to green and blue, it will keep the color regardless. However, when it comes to red, anything that is below 0.8 is going to be removed. So now when we run this, we'll find that we still have a little bit of unwanted extra colors. So let's reduce the bounds slightly and make this 0.1. So now we just have the red color, which is the red distinct color of the dome. So the next step that we have to do, we have to do something that's called a blob detection or a connected component. This process will look at your color, and actually right now this is a binary image, meaning we have everything here at 0 and here we have a bunch of 1s. So the blob detection looks at your image and then tries to find the components that are connected to each other. And in this case we only have the one object, but if we had more than one object, then it would return more than one blob. So blob detection on work image, and if we add this filter and we move it up above here, we'll find that now, let me just run it and pause it. Here it draws a bounding box over all the blobs that it detected, and it assigns them a value. Right now this is blob number 1. If you double click on the blob detection, you will find that well, a couple of options. Here you are given a threshold, and this threshold kind of allows you how easy it is for a blob to be detected, and I encourage that you play around with it and see what happens. And here it will also say, give you the function return values. So it will return a packet which it will append to a function that I will talk about it in a little bit, and it will return the following values. The first one will be the blob count, so how many objects did it detect. The second one will be how many values you have per blob count, and the one thing that we will be really interested in is at 5 and 6 it will have blob 1 position X and blob 1 position Y. Alright, and then now we can close this. So now you have modeled a path, a moving target, you were able to model the camera, and now you've done blob detection. Now you have to implement the control scheme in the code itself. So now that we have all of our components, let's write the code for the visual servoing scheme. First thing we have to do is we have to add a script to the vision sensor. So right click on the vision sensor and select add, and then associate a child script, and then here you get the option of threaded versus non-threaded. Since in visual servoing this script will be continuously running and it will update the velocity of the camera repeatedly, we select a threaded script. So now this icon appeared and it showed us that it has a script. When you double click on this icon, you will see the child script associated with the vision sensor. So here you have kind of two general modes or two general areas. The first area up here is initialization code. This is something that's going to be run just the one time. And down here you have the looping code. So this code is going to be looped through over and over again and run repeatedly. So because you have well, whenever you're writing kind of large and complicated scripts, you want to know what's going on the inside, and you want to probably have some form of a debug console. So this is where these things that are called simAuxiliaryConsole come in. So let's put right here a handle to a auxiliary console. And you select the open, and then when you open the bracket it gives you a whole bunch of things, a whole bunch of options for the input. So the first thing it wants is a title, and we'll just call it debug. And then the second option will be number of maximum lines, and we'll arbitrarily set it to 8. And then comma 1. Alright, so now if you run your script, this debug console comes up. The next thing we want to do is we want to write to this console. So we use the ConsolePrint function. So here we just say simAuxiliary CoppeliaSim.CoppeliaSim.ConsolePrint, and what it asks is the handle to the object, which we select as out, or you can call it something up here, something more imaginative, and then the text. So for now, let's start a new line, and then I don't know, just like a hello world. And now when you run it, it just keeps printing hello world, and it has 8 lines. So nothing really crazy happened here. The next thing we're going to have to do is get handles on all of our joints, as well as on our vision sensor. Let's rename the vision sensor, and then we'll call it cam. So to get a handle, you just write, well, whatever handle, whatever you want to call the handle, and then sim get just a second, sim get object handle, and then here you give it what you called it in your scene hierarchy. So the argument will be just yaw. And then we do the same thing for the pitch. And then the same thing for the camera as well. Get object handle. So, and let's run it and see whether it works so far. And down here you will get information about, well, if whatever script you're writing has any problems. So we should be good for now. So now we're going to have to deal with the camera. So to read the vision sensor, we have to first, let's consult the help file. So when you select help and select help topics, it will open up the VREP user manual. So over here, select entities, and then scene objects, and vision sensors. So in the vision sensors, when you scroll all the way down, you'll get these recommended topics that say related API functions. That will show you all of the functions that are associated with that object. And it's good to keep checking the user manual to find out the full capability of the objects that you're working with. So the thing that we're interested is the following function. It's simRead vision sensor. All right here. So then you get this option where you, well, first of all, there's a description, and we're using luau because we're working in the script. Over here, it will tell you what kind of the syntax of the command. So the first thing it's going to return is a number and a result. This result will be 0, 1, or -1 if there's an error. And then what is going to be, the next one is going to be various vectors full of packets. And these packets depend on what kind of a filter you have associated with your camera. So in this case, we find out that all we have to do is we have to write it in the following form. Well, first we have to assign a couple of variables. So let's go back to VREP and then begin by reading the vision sensor. So here I'm just going to copy and paste this from my notepad. So here we're reading the camera and we're storing the results in results, which will tell us if it was successful or not. And then here we have the first packet, which is always associated with the vision sensor, simRead vision sensor. And then here is the second packet. This second packet we get from the fact that we're using blob detection on work image. So this second packet is going to have all of these as vector entries. Alright, so now let's find the x and the y value of our target, which I will call x, well, let's call it x target, and then y target. Alright, so now we would like to actually print these in our debug window, just so that we can kind of see what's going on. So since we're trying to use variables within our string, let's use the string.format command. And I'll just kind of copy and paste sample code to reduce the size of this video. So string.format, and then here we have the string.format command takes in a string, and whenever you want very similar in C or C++, it allows you to add these descriptors of what your variable, what form your variable is supposed to take. So here let's add what we want to do is we want to give out the x and the y, and we want to have x target and y target. So now let's try running it and see if we have any errors. Okay, so here it tells us that in line 45 we have some sort of an error, and I can see that there is a bracket missing. Okay, the other thing that I forgot to add is a line break for a new entry. So now when we run it, we see that x and y change. Alright, so let's try running it again. So here x right now is 0.92. So this tells me that our I guess the way it stores the variables is from 0 to 1, and currently our y is decreasing, so it has actually the origin right here at the corner. So next, now that we have the target location in the image, now let's adjust the joint velocities of the rotating joint to actually follow the target. So to implement our visual servoing control scheme, we have to use the following command: sim set joint velocity, target velocity, and then here it asks for a handle, and let's try just using yaw for now. And then the next thing is going to ask us is our target velocity. So let's implement a proportional control law, meaning well, we want our object to be in the center of the image. Alright, now the yaw moves it in the x direction. So what we want to do is, if the target is very far away from our center point, we want the velocity to be very fast, meaning we want the joint to move very fast towards the target. And as it gets closer and closer, we want to reduce the velocity until it's at the center. So this is just a simple proportional control law. So let's implement just kind of 0.1 for now times, and let's say 0.5 minus x target. Alright, and now let's see what happens when we run this. And now, as you see, actually, let me move this out of the way and restart it. So now you can see that the camera is trying to keep up with the object, but then it leaves the image. So one thing we can do, well, first of all, we haven't implemented pitch yet. However, one thing we can do is actually increase our proportional gain. So what we do here, rather than 0.1, let's try just making it 1. And let's see whether it's even properly working yet. So now it actually keeps up with the target. And let's see whether it just doesn't overshoot. Yep, and now you can see the velocity decreases, and now it actually pans back. And let me show that to you again. So now it actually is tracking it in the X direction. However, it still doesn't do anything about the Y direction, so let's fix that. So we'll need to use the same command, except rather than yaw, we'll say pitch. And we don't know whether we still need a negative, because it really depends on how it was defined. So let's try 1 minus y target, and then let's run it and see what happens. So now you can see that the camera moves up and down and actually follows the target pretty well. So now we have an object moving in a field, and we have a camera tracking it. So let's try to actually see what else we can do here. Well, first of all, this right here is nice. We can kind of see that the target object is in the image. However, we would like to probably see the actual image. One thing that you should note is that because we have a moving target and we're using just a simple proportional control law, you can actually see that the camera is lagging the target. And this is because we're just using a simple proportional controller. If you added, for example, an integral portion as well, you would find that it could reduce the error to 0. Alternatively, if you wanted to reduce it, you can actually increase this proportional gain, and it would still be there. However, it would be a lot smaller. So if you run this now, you will find that it's actually kind of spot on. However, it's still lagging a little bit to an unnoticeable degree. Okay, so the next thing that we want to do is we want to see the actual image of what the camera sees. So here, let's go in the show filter dialog, and what happens here, we have these two operations that are being performed, and then at whatever the output of this is going to be the output image. So let's move our output image up a little bit, and now you can see that now you actually see what the camera sees. However, all of these operations are still performed on the image. Alright, so the other thing that we would like to do is we would like to visualize the velocity of the camera. So the way we do that, let's add a new view. Select add floating view. We would like to just kind of graph the velocity as a function of time, just to see what's going on. So we have a floating view. Now let's add a graph to the scene as well. Select add and then graph. And when you double click on the graph, here you select add new data streams to record. And here let's select under joint, we want the joint velocity, and it gives us two objects. One for them will be yaw, and let's rename this to, I guess, yaw. However, let's also change the color as well, adjust curve color, and then let's make this maybe just a blue. And then let's add the other object, which is the other joint velocity, which will be pitch. So this will be pitch, and then it'll be assigned by default a red color, and that's fine. So with the graph selected, let's right click the floating view, select view, and then associate view with selected graph. So now when you run it, you can actually see the velocity as a function of time. The interesting thing to note well, it's kind of going on, and this is going to just kind of graph to you the velocity. Let's make the object stationary, and by double clicking on the path and then select 0, and then let's see what kind of conversions we get when we run this. And you will find that it's actually a asymptotic convergence. However, something interesting happens here. Let's reduce the velocity or the proportional constants to 0.1. And you will see that you will get this nice exponential decay because you're using a proportional control. So, and the rate of convergence will depend on your proportional constant right there. If you set it way too high, that's why we were getting these weird overshoots, because the motion of one degree of freedom was affecting the motion in the other. All right, and that's pretty much it. Let me just kind of run it again. And yeah, thank you all for watching. And if you have any questions, please post your questions in the links below. And yeah, I hope you enjoyed these videos. And if you have any suggestions for other videos, please contact me again. Thank you very much.